order of operations. It's funny. I just saw a teacher teaching order of operations when I was binging Ozark season 3. It was right in the beginning of the season. And he explained it the exact same way I explain it, and the exact same way I think everybody's teacher has ever explained it, which really helps. Order of operations can be summed up with the sentence, "Please excuse my dear Aunt Sally." Please excuse my dear Aunt Sally is a mnemonic device. Please excuse my dear Aunt Sally, to help us remember PEMDAS, which is not a word, but that is another way that people speak of order of operations, PEMDAS. Parentheses, exponents, multiplication, division, addition, subtraction. It looks like it's 6 steps, but it's not. It's actually 4. Multiplication and division is actually 1 step. Left to right, multiplication and division as you come to it in your problem. Addition and subtraction is 1 step. Addition and subtraction from left to right as you come to it in your problem. Step 1, P, parentheses. We work inside parentheses. If we have parentheses in the problem, ignore everything outside until we have simplified what is inside as much as possible using the order of operations. Then when there's nothing left to do inside parentheses, evaluate any exponents you have. So any squareds, any cubes, go ahead and simplify those. Then from left to right, any multiplication or division that you come to. And when you're done with all of that left to right, you'll only be left with addition and subtraction. You go back and you go left to right. So let's look at an example. Let's look at many examples. Well, let's simplify 2 times 4 minus 3 divided by 3. We do not want to just work left to right. We will get the wrong answer. 2 times 4 is 8 minus 3 is 5 divided by 3 is 5/3, a fraction. The way we're doing this class, we don't even know what a fraction is yet. PEMDAS, the order of operations, tells us do parentheses first. We have none. Then do exponents. We have none. Then multiply or divide in order from left to right as we come to it. So from left to right, here's a multiplication problem. 2 times 4 is 8. Write the rest down. 1 step at a time. So then we go 8 minus 3. We don't do that. We're looking for multiplication or division. 3 divided by 3. Yes, 3 divided by 3 is 1. So this is 8 minus 1. And then finally, 8 minus 1 is 7. 7 is the correct answer, not 5/3, whatever that is. Here are 2 problems, order of operations, I'd love you to try. 48 divided by 3 times 2 squared, and 10 minus 7 to the 4th power plus 2 times 3 squared. Go ahead and try these. Fourth power and a squared. Okay. So on the left, if we're doing PEMDAS, no parentheses, so we do the exponent first. 48 divided by 3 times 2 squared is 2 times 2, that is 4. Then multiply or divide from left to right. 48 divided by 3 is going to give you 16. And then 16 times 4. In fact, let me show this work. 48 divided by 3 is 16. 16 times 4 is 64. Okay, if you haven't finished the second one yet, go ahead and pause because I'm going to do that right now. Parentheses first, 10 minus 3, or sorry, 10 minus 7 is 3 to the fourth power plus 2 times 3 squared. 3 to the fourth power is 3 times 3 times 3 times 3, which is 9 times 9, which is 81. Plus 2 times 3 squared is 3 times 3, that's 9. 81 plus 2 minus 9 is not 83 plus 9. We have to do multiplication first. So 2 plus 9 is 18, and 81 plus 18 is 99. 99 is the correct answer. Okay, let's work on this one together. We have 4 cubed, 4 to the third power, plus, in brackets, 3 squared minus, in parentheses, 10 divided by 2, minus 7 times 3. So, parentheses first, and we need to go to the innermost set. So 10 divided by 2 is 5. Write everything else except that 10 divided by 2 is now a 5. Everything else is the same. Then we have these brackets. They're now the parentheses we're looking at. And inside of there we have to do 3 squared is 9. Everything else stays the same. 9 minus 5 is 4. So this is 4 cubed plus 4 minus 7 times 3. Exponents. We're done with parentheses. Exponents. We've done some exponents, but they were inside parentheses. 4 cubed is 4 times 4 times 4. 16 times 4 is 64. 64 plus 4 minus 7 times 3. We have to do the multiplication next. 64 plus 4 minus 21. Then addition and subtraction from left to right. 64 plus 4 is 68. Minus 21. Our answer is 47.
Okay, remember the fraction bar counts as parentheses. We're going to split this from a top problem and a bottom problem. And the bottom is just one step. 3 squared is 9. On the top, 6 plus 9 divided by 3, just so we could see that better. The division has to be first. 9 divided by 3 is 3. So this is 6 plus 3 over 9, which is 9 over 9. And finally, 9 divided by 9 is 1. Go ahead and try this one. This says 81 divided by the square root of 81 times 5 plus 7. Okay, so first, the square root of 81 is 9. Everything else gets written down. Multiplication and division from left to right. So 81 divided by 9 first, that's 9. Then the multiplication before the addition. 9 times 5 is 45. Plus 7. Our answer is 52.
We're going to do something new, but at the same time, we've done it all before. We've literally done it all before. The only difference with what we're doing today is that we will have decimals. Decimals, that period, that point that is in some numbers, like 2.5. Now, 2.5, that's not how we will actually say this. This would actually be 2 5/10. What does this mean? How do we know this? Well, to start with decimals, we have to start where we started with whole numbers. Just a few short classes ago, we learned ones, tens, hundreds, thousands. Remember the place value. Well, it turns out that there's more place values to the right of ones, and they mirror what's going on the other side. We have tenths, THS instead of S. We have hundreds, THS instead of S. What goes to the left of hundreds? Thousands. And sure enough, over here, we have thousands with the THS. Ones, tens, hundreds, thousands, 10,000s, 100,000s. How about 10,000ths? With the THS. And 100,000ths with the THS. So ones becomes like a mirror. And to the left, we have our place values we know already. Tens, hundreds, thousands, 10,000s, 100,000s. To the right, we have the mirror image of that, but instead of S, we have THS. Tenths, hundreds, thousands, 10,000s, 100,000s, millionths, 10 millionths, 100 millionths, billionths, 10 billionths, 100 billionths, so on and so forth. And separating the ones from the tenths is not a oneths spot. It is a decimal point. So how do we say a number? Well, how about 14.23? You're thinking, well, you just said it, 14.23. And yeah, we'll say that. But that's for simplicity. That's not what this number is. Just like you and I still slip and say things like 394 instead of 394. Or that one's kind of bad, actually. And you'll see why in a second. More like the way we say 204 instead of 204. We don't even say 204. We say O. O is a letter. 0 is the number. We should be saying 204 instead of 204, not 204. Anyway, I said that the 194 is actually pretty bad. That's because the decimal point is literally spoken as the word and. So if you ever say and in a number and don't mean the decimal point, you're saying the number wrong. How do we say the full number? Well, to the left, since we just learned about this right side today, obviously we know how to say the number 14 or whatever is to the left of the decimal point. We say it. So step one, we say 14 because we see that to the left of the decimal point. And then we say and because of the decimal point. That's how we say it, and. And then they come and cart us away because we're doing cheers for 14.23. Okay, problem ran away. Don't worry, I brought it back. I also fixed the framing a little bit. In case you didn't see, I wrote decimal point up here earlier. So, and that's how we say the decimal point. Now everything's fixed back in the frame. After we say the number to the left of the point and we say and for the point, then we say the number to the right of the decimal point, 23. 23. And then the last step in saying a decimal number properly is looking and seeing where the place value ends. So we said 23. Where does the 23 end? It ends in hundredths, tenths, hundredths. And so we say hundredths. $14 and 23 hundredths. 14 and 23 hundredths. Let's do another one. $372.002. Well, how do we say this? 372 decimal point. And how do we say 002? 2. And where does it end? Thousandths. $372 and 2 thousandths is how we say this number properly. And now I'm putting quotes around each of these so you can see the 1, 2, 3, 4 steps. 1, 2, 3, 4 steps. But obviously, the number itself, 372 and 2 thousandths, would all just be written as one thing. And we'll do that in the next example. We'll just write it as one thing. $504.9. 504.9. This would be 504, not 504, because where does the and go? Point and 9 tenths. $504.9. And we should be able to go the other way as well. And you're saying, wait, what? The other way? Go the other way. $5 and 7 tenths. Well, the and is the decimal point. 5 must be the number we write before the decimal point. And then we can't just start writing 7. What we have to do is look at where it ends. We see it ends with tenths. We have to identify the tenths place and make sure the number ends in that spot. So 5.7, there was no worry there. But that's not always going to be the case. Let's take a look at 3 and 2 hundredths. Well, the and is the decimal point. 3 must be what we write to the left of the decimal point. 2 hundredths. We can't just write 2 because that would be 2 tenths. So we have to see hundredths. We have to identify hundredths. It's the second one. And we have to make sure the number 2 ends there. So what do we fill in to keep the space? A 0. 3.02, 3 and 2 hundredths. To the left, if we had, let's say, a 0 there, and not even let's say a 0, this whole thing only works, what I'm about to say, if there's a 0 there. This 0 is optional. Here's why. If we wrote 0 and 2 hundredths for 0.02, well, that would be the same as just 2 hundredths. Because 0 and 2 hundredths is like 0 plus 2 hundredths, and anything plus 0 is itself. So we wouldn't say 0 and 2 hundredths. We would just say 2 hundredths. And since we don't have a number, you don't necessarily need a number before the decimal point. Now, we wouldn't just say and 2 hundredths either. In this case, the decimal point is silent. 0.02 is 2 hundredths. We know there's a decimal point there because we're saying a number that ends in THS, and those are exclusively for to the right of decimal points. So even though we don't see 0 and we don't see and to say put a decimal point there, 2 hundredths, since it ends in THS, would have an implied decimal point because we need to be here in the hundredths THS place value. Okay, so now we know how to say and write decimals. Let's order them now. Let's figure out what's less than and what's greater than. If we had 0.63 and 0.68. So if we had 63 hundredths and 68 hundredths, we would like to know whether these are able to be compared with this symbol, with this symbol, or with this symbol. This one is less than. This one is greater than. This one is equal. The way you can keep less than and greater than straight is that the L in less, when you tilt it, makes the less than shape. Less. See it? I like to remember it by using our old friend Pac-Man. Yes, Pac-Man from the Pac-Man game starring Pac-Man. Pac-Man is hungry all the time. He likes to eat. If given the choice between the number 1 and the number 2, Pac-Man would choose to eat the number 2 because it is more than number 1. And when you like to eat a lot. So you can remember Pac-Man always chooses to eat the larger number. So 1 is less than 2. This way, the greater than symbol, 2 is greater than 1. How do we know? Because Pac-Man would choose to eat the 2 every time. 2 is greater than 1. And we know what equal means, that they're the same. So when we're comparing decimals, we want to take it digit by digit. Obviously, if we just look at the numbers before the decimal point, if they are different numbers, it is a very easy problem to do. However, when they are the same number, we have to go place value by place value. So 0 point, they're the same so far, moving over. 6, they're the same, moving over. 3 and 8, these are different. They're the first one that's different, so they're what we will compare. Since 3 is less than 8, 0.63 is less than 0.68. Let's compare more numbers. 0.35 and 0.32. Zeros are the same. 3s are the same. 5 and 2 are different. Compare the 5 and the 2. 5 is greater than 2. So 0.35 is greater than 0.32. You're thinking, okay, this is pretty simple. Don't fall for any tricks. 0.297 and 0.3. Maybe a rushed reaction would have you go, wait a minute, this has so many more digits than this one. This one must be greater than, but that would be wrong. Because remember, we have to go digit by digit. It doesn't matter how many we have. What matters is the zeros are the same. The first number that's different is this 2 and this 3. That is what we compare. 2 is less than 3. So 0.297 is less than 0.3. And that makes sense because 0.3, it doesn't matter how many zeros we have afterwards. That's something that's fun about decimals. We can keep adding zeros. We can keep adding zeros and not change the value. So when it's 3 digits compared to 3 digits, we see 297, we see 300. 297 would be less than 300. So we can't just compare looking at 297 versus 3, because 297 would be bigger than 3. We have to go digit by digit, because that will give us that situation, the same answer as the situation where we can clearly see 297 and 300. If you want, when you see a comparison like this, if this is 3 digits and that's 1 digit, go ahead and put zeros in. Help yourself out. But still, show that you're comparing these. Okay. Now that I've said all that, 0.514 compared with 0.51400. Don't be fooled. We've got 3 digits here. We've got 5 digits here, but the last 2 are 0. Let's match that with a couple zeros over here. And what do we clearly see? We clearly see that these are equal. it didn't matter that this only had 3 digits past the decimal point, and this had 5 digits past the decimal point. What mattered was the zeros were the same, the 5s were the same, the 1s were the same, the 4s were the same. These zeros at the end don't matter. And if we match them up here, the zeros are the same, the zeros are the same. So equals. So for our next one, let's say we had 3 decimals, okay? 0.0033, 33 tenths, hundredths, thousandths, 10 thousandths, 33 10 thousandths, 0.033, 3 tenths, hundredths, 3 hundredths, and 0.003, 3 tenths, hundredths, thousandths, 3 thousandths. We want to put these in order from smallest to largest. So let's compare them. Notice I wrote them with decimal points right in a row so I can see each digit. Before the decimal point, 0, 0, 0. They're all the same, so it's not going to matter when it comes to ordering. After the decimal point, 0, 0, 0, all the same. Not going to matter when it comes to ordering. Here is where we have our first difference, 0, 3, 0. Now we can't differentiate between the 2 zeros, but 3 is greater than both of those. So 0.03 must be the largest. Let's keep going. 0 and 0, they're the same. They don't tell us anything. We move on. 3 and 3, they're the same. They don't tell us anything. We move on. 3 and, nothing. Well, what can we fill that in with? 0. 3 and 0. The 3 is bigger. That means this one is the smallest. So here, 0.0033, that's the middle. And the smallest, 0.003. In the homework problem, you're literally going to drag them and put them in the proper order. Okay, so we can compare, we can put things in order. I guess it's time to talk about adding. So remember all the rules for adding and all the adding we did in class and all the adding we did in the so much review we've had? I'm only going to add one rule. Line up the decimal points. So if we have 6.7 plus 3.2, to add these, we line up the decimal points and add like normal. Where the decimal points are in the problem is where the decimal point goes in the answer. 7 plus 2 is 9. 6 plus 3 is 9. 9.9 would be the answer. That's all there is to it. It's just like adding. We just line up the decimal points. 7.4 plus 5.16. Line up the decimal points. 7.4, 5.16, and then add. If you have empty spots due to lining up the decimal point, what can we fill it in with? What do you think? 0. So line up the decimal points, decimal point into the answer. Add like normal. 0 plus 6 is 6. 4 plus 1 is 5. 7 plus 5 is 12. 12.56. So how about 107.563 plus 42.07? Line up the decimal points. 107.563, 42.07. So much interesting happening here. We have an extra place value. We can fill in a 0 there. And when we do our adding like normal, we'll have carrying. 3 plus 0 is 3. 6 plus 7 is 13. Carry the 1. 1 plus 5 is 6. 7 plus 2 is 9. 0 plus 4 is 4. 1 plus nothing is 1. 149.633. I can't really make that more interesting, it turns out. I guess what I should mention, just to be clear about it, is if we had something like 470 plus 53.11, we don't see a decimal point in the first number. But we know that the decimal point exists at the end of the number. So 470 is the same as 470.0 or 0.00, as we're going to need here to line it up with 53.11. But after that, it's just our normal addition. Just like with regular addition, if we're asked to find the sum of something, that means add the numbers. Subtraction is going to work the exact same way. Line up the decimal points, subtract like normal. 11 minus 7.5. Well, just like with that addition one, when we don't see a decimal point, we know it exists at the end of the number. So 11 is 11.0. Minus, line up the decimal points, 7.5. Decimal point goes where it goes in the answer. Line it up. And then subtract like normal. 0 minus 5, we can't do it. What do? We borrow. That 1 becomes a 0. This 0 becomes a 10. 10 minus 5 is 5. 0 minus 7, we can't do it. We borrow. That 1 becomes a 0. This 0 becomes a 10. 10 minus 7 is 3. 3.5 would be the answer. We can check with addition if we want. Add up 3.5 plus 7.5, and what do we get? 11.0, which is 11. So 3.5 is the answer when we subtract. Let's do another one with subtraction, bigger numbers, missing digits. 565.3 minus 56.02. So I'm giving this one to you lined up already. We have a missing digit here. In order to do our subtraction, we need to see that that is a what? A 0. And except for putting that decimal point in the line, it's a straightforward subtraction problem. 0 minus 2, can't do it. Borrow, 3 becomes a 2, 0 becomes a 10. 10 minus 2 is 8. 2 minus 0 is 2. 5 minus 6, can't do it. Borrow. 5 becomes a 15. 15 minus 6 is 9. 5 minus 5 is 0. 5 minus nothing is 5. 509 and 28 hundredths. 509.28. How can we check it? We can check by adding. 509.28 plus, line up the decimal, 56.02. 565.3. That's what we started with. So we know we're right. Let's give one that's not lined up. Work that out. We'll check by addition when we're done. 900 minus 6.1. Well, that's 900.0 minus 6.1. Borrow. These zeros become 9s. A 9 becomes an 8. 10 minus 1 is 9. 9 minus 6 is 3. 9 minus nothing is 9. 8 minus nothing is 8. 893.9. And if we add the 6.1 to the 893.9, we get 900. So we got the right answer, 893.9. So because of the fact that the decimal points need to be lined up, and it's not always going to match up with the same number of digits, that means that there will often be cases where we are filling in missing zeros. And that means that there's going to be a lot of subtraction work that has to do with borrowing and zeros. So if that was a struggle with subtraction for you, that struggle is going to become real. So you'll be able to say the struggle is real. Let's look at this one. 8 minus 0.0023. When we line it up, that would be 8 point. We need 4 of them. 0, 0, 0, 0. Minus 0.0023. Why did I put all those in there? Because 8 minus this decimal, the decimal has to line up, which means it's 8 point. And because of all these blank spaces, I need to fill them with zeros, which means the subtraction is going to be involving 0. We're going to borrow. 8 becomes a 7. All the skipped zeros become 9s, and that 0 becomes a 10. 10 minus 3 is 7. 9 minus 2 is 7. 9 minus 0 is 9. 9 minus 0 is 9. Decimal point. 7 minus nothing is 7. And if we add the 0.0023 back, we get 0, 0, carry the 1, carry the 1, carry the 1. We get 8. 7.9977 is correct here. We checked by adding. We got the right answer. Our favorite type of subtraction, word problem. Subtract 7.3 from 16. Same as before. When we're subtracting something from something else, we have to think it through. What are we starting with? We're starting with the 16. We are subtracting 7.3 from that. And notice how I set it up. Since 16 would be 16 point, that lines them up. fill in a 0. Subtract, borrow. 10 minus 3 is 7, decimal point. 5 minus 7 can't do it, borrow. 1 becomes a 0, 5 becomes a 15. 15 minus 7 is 8. And if we check by adding, 8.7 plus 7.3 is 16. Got the right answer. 8.7 is it. Why is it important to think this through and not just go, well, clearly it's 16 minus 7.3. The 16 is bigger and therefore it goes on top. I give you a little accent there. Because in the future, at the end of the course, we're going to be doing these with negative numbers. So 7.3 minus 16 will be just as valid as 16 minus 7.3, and it will be up to you to figure out which one is the correct answer, which is why you need to know now. Subtract this from that means you're starting with and subtracting from it. Okay, so we've done addition. We've done subtraction. I think we're ready to talk about multiplication. So for multiplication, you are going to forget about the rule of lining up the decimals. Okay, lining up the decimal points, that is just addition and subtraction. Multiplication and division, you set them up just like a normal problem. So let's say we had $2.31 times 9.4. Ignore the decimal points. Just ignore them entirely. If it was 231 times 94, we would just set it up like this. So that's what we do. Notice the decimal points are not lined up. Do not go out of your way to line them up. If they happen to line up, they happen to line up. But that does not mean that that's where the decimal point will be in the answer. We'll get to where the decimal point will be in the answer after we're done multiplying like normal. 4 times 1 is 4. 4 times 3 is 12. Carry the 1. 4 times 2 is 8, plus 1 is 9. Moving over to the 9. 9 times 1 is 9. 9 times 3 is 27. Put down the 3, carry the 2. 9 times 2 is 18, plus 2 is 20. And then we add. 4 plus nothing is 4. 2 plus 9 is 11. Carry the 1. 10 plus 7 is 17. Carry the 1. 1 plus 0 is 1. 2. Now the answer is clearly not going to be 21,714. In fact, if you look at the numbers we multiplied, 2.31, that's about 2. 9.4, that's about 9. So 2 times 9, that's about 18. So 21,000 doesn't make sense. 2,171 doesn't make sense. 217 doesn't make sense. 21 is awful close to 18. That's the closest. In fact, we'd expect it to be there based off of estimating that that's about 9, and that's about 2, and that's about 9. So the answer will be about 18. Here's how we find where it goes. How many decimals, or how many places after the decimal points did we have in the original problem with both numbers? 1, 2, 3. There were 2 after with this one. There was 1 after with this one. 2 plus 1 is 3. So the answer needs to have 1, 2, 3. Sure enough, that decimal point does go there. And the answer is 21.714. Let's do another. Let's take a look at 0.194 times 0.7. Seven times 4 is 28. Carry the 2. 7 times 9 is 63. Plus 2 is 65. Carry the 6. 7 times 1 is 7. Plus 6 is 13. Carry the 1. 7 times 0 is 0. Plus 1 is 1. And then here, 0 times everything would just be 0. Add 8, 5, 3, 1. And count 1, 2, 3, 4 digits past decimal points. 1, 2, 3, 4. So the point would go here. We can have our 0. Our answer would be 0.1358. Now, when you're doing this, taking into account that zeros in front of the decimal, if that's all that's there, remember they're not needed. We could just do 194 times 7, have our decimal points there, and just do this work. 7 times 4 is 28, 63, 65, 13. 1, 2, 3, 4, 1, 2, 3, 4, 0.1358. If you so choose, you can put a 0 in front. Take a look at this one. 492.8 times 0.065. 5 times 8 is 40. 5 times 2 is 10. Plus 4 is 14. 5 times 9 is 45. Plus 1 is 46. Carry the 4. 5 times 4 is 20. Plus 4 is 24. Done with those. Moving on to the 6. 6 times 8 is 48. 6 times 2 is 12. Plus 4 is 16. 6 times 9 is 54. Plus 1 is 55. 6 times 4 is 24. Plus 5 is 29. We could do 0 times all of that. We could do 0 times all of that, or we could just ignore that we have these zeros and move on with our day, as it were. Four plus 8 is 12. 13, 10, 12, 3. So it looks like before we put the decimal point in, we have 320, 320. Where does the decimal point go? What's our last step? What's the new thing for multiplying decimals that we didn't do before? It's the counting 1, 2, 3, 4. The counting of how many places we have to the right of decimal points. So 1, 2, 3, 4. 1, 2, 3, 4. 32.0320 would be the correct answer here. So addition and subtraction. Line up the decimal points, add or subtract like normal. Multiplication, do not line up the decimal points. Multiply like normal, and then do that counting at the end to figure out where the decimal point goes. Division, that's going to have its own set of rules. But before we get there, now that we've talked about how we should not line up the decimal points, I did mention sometimes they do happen to line up on their own. And that's okay. But that does not mean that the decimal point is in the same place in the answer. For instance, if we had 2.3 times 3.1, look, the decimals just happen to line up. And that's okay. But where is the decimal point going to be in the answer? 2 spaces over, because of these 2 spaces total past decimal points. 1 times 3 is 3. 1 times 2 is 2. 3 times 3 is 9. 3 times 2 is 6. Add 3, 1, carry the 1, 7. But it's not 713. It's 7.13. Okay. You may have heard something like this before, 1.6 billion. Well, do you know what that means? We can use the decimal point as a sort of time saver when saying really large numbers that have a lot of zeros in them. 1.6 billion would be 1,600,000,000. And that's it. 1,600,000,000 is how you say this really long number, because this grouping is ones, tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions. Since this first comma is a billion, if we replace it with the decimal point and erase all of the zeros at the end, we can just say that. So instead of 1,600,000,000, we can just go 1.6 and get rid of all those zeros. And what was that comma? It was a billion. 1.6 billion. So we can write really large numbers like that. How about 46.4 million? How would we write this as a number? Well, thinking about that logic, if this point is here, that means it's where the millions would be. So it should be 46 million and then a 4. The rest would be zeros, but if this is 46 million, that means that 4 has to be 100,000. So 46,400,000. Now that we know everything we need to know about multiplying decimals, when we multiply length times width, what is that? That's area of a rectangle, length times width. If we had a square, what makes a square and not just an ordinary rectangle? Because we could still do length times width to get the area, but it's that all the sides are the same length. So for a square, you just have one side length, and that's all four sides. So for perimeter, you would multiply the side by 4, because that's the same as repeatedly adding that plus that plus that plus that when all four are the same thing. So the area of the rectangle formula tells us that an area of a square would be side times side. What do we call it when we multiply something by itself? We call it squaring. Side times side is side squared. Side what? Squared. Area of a square. Square. That's where that comes from. Remember, I showed you how area is all the different 1x1 squares you can fit on the inside of a thing. So why are we waiting until now to talk about how the area of a square is just side squared? Well, because measurements are not, they're not unique. They're not always going to be, exactly 3. When you take a measurement of something, you're going to get 3.1. You're going to get 4.7. You're going to get 129.03. So you're not always going to be working with whole numbers. In fact, you're rarely going to be working with whole numbers. So let's say we have a square. And the side of this square is 2.3 meters. What is the area of the square? So we would multiply 2.3 times 2.3 because this would be 2.3 squared. 2.3 times itself. 2.3 times 2.3. 3 times 3 is 9. 3 times 2 is 6. 2 times 3 is 6. 2 times 2 is 4. Add 9, 12. Carry the 1. 1 plus 4 is 5. 2 decimal points, or 2 places past the decimal point. 2.3 squared is 5.29. And in this case, we would have meters squared as well, or squared meters. Let's say the area of the square was just, or the side of the square was just 0.3 meters. Or 0.3 meters. Same thing. Well, 0.3 times 0.3 is not 0.9. 3 times 3 is 9. But notice 2 spaces past the decimal. So 1, 2 spaces have to be there. So the area would be 0.09 square meters. So for the area of a rectangle, you do length times width. And then if it's a square, that becomes side square. But it's still length times width.